Thank you all for joining us. Today, as you just heard, isn't about quantum hype or distant science fiction. It's about what quietly is taking shape right now. That's sensing, navigation, policy, materials, security. The parts of quantum that are already reaching society that are much further along than the compute side or hardware, as most of us know it by. I'd like to begin by inviting my panelists to introduce yourselves. Briefly share what part of this future you're helping to build. And Ryan, if you would kick off.
Sure. Hi, everyone. My name is Ryan McKinney. I am the General Counsel of Compliance and Director of Government Relations at a company called Quantinuum. We are a spin-out from Honeywell about 4 years ago, and we make quantum computers and the software, hardware, and middleware that allows you to code your problems onto a quantum computer and work with a lot of different industries and government partners as well.
Hi, everyone. I'm Jamil Bashair. I'm CEO and co-founder of Vector Atomic. We're a company based in Pleasanton, California. We make atomic clocks and atomic inertial sensors, very precise sensors to measure rotation and acceleration for navigation, communications, and geophysical exploration. Our company was recently acquired by IonQ. We're very excited about that because it's going to give us an opportunity to take the technologies that we have put out into the world and productize them and really bring up production to kind of accelerate their adoption in the market.
Hi, my name is Amanda Stein. I am the CEO of a company based in College Park, Maryland, right outside of the University of Maryland, called Quantum Catalyzer. We're a research and development organization commercializing quantum sensors. We work on next generation sensors and applications thereof. And when we see an application and a fit coming out of our research, we spin out companies. So we also act as a venture studio. To date, we've spun out 2 companies. I'll talk a little bit more about that during the panel. And hopefully in the future, we'll spin out several more.
Hello, everybody. My name is Jeffrey Whalen. I'm the founder and CEO of Magnetics Corporation. Primarily what we do is build superconducting magnets, and we operate a joint technology development department as well as an economic development department in superconductivity and magnetism. And we found our way into quantum really through multiple parallel streams in what we do, which primarily is building large superconducting magnets. But in the areas of energy and compute and medical and manufacturing, we've found our way into quantum in control magnets and shielding magnets and cryogenics, as well as hybrid supercomputing quantum systems. So very happy to be here and share with you all.
So we're already hearing lots of words that some people take for granted, and some people are saying, what in the world are you talking about? So Amanda, quantum sensing. You are pushing forward with quantum sensing. Why now, and what motivates you to do this? And break it down for us a little bit more.
Yeah, so maybe first we'll start with actually what is a quantum sensor. And we hear this term quantum. Really what that means is bringing things down into a subatomic level. So think about the sensors that are looking for fire, the sensors that detect if water is clean. Those are all sensors that are using classical physics. Our quantum sensors are bringing things down to the subatomic level, and why that's important is that you can get higher sensitivities. You can be able to detect things that you may not have been able to detect before, such as levels of magnetic property, and go into more extreme environments such as space, as we talked about a lot today, or out on the energy grid. So we believe that that is here now because the actual technology that we've been working on has been worked on for 20 plus years. The technology of quantum sensors is advanced what is in quantum computing at this point, and to the point where we're starting to deploy quantum sensors out into the field for whatever application that sensor is going for.
And so, Jamil, you're also on the sensing side, but more positioning and navigation. Can you tell us a little bit more about what a real application that we would understand looks like?
Sure, and I think everyone thinks quantum technology is 10 years out, maybe 20 years out, but quantum technology has already arrived, and it's being used by all of us today, whether we know it or not. The prime example is the Global Positioning System, GPS, tells us where we are on the planet to about a meter. We're all using that in our daily lives, whether we're ordering Uber Eats or we're getting packages delivered to our homes. that GPS technology is fundamentally a precision timing network based on a bank of atomic clocks on the ground and atomic clocks in space that are all transmitting timing in 10 nanosecond increments, 10 billionths of a second. That's what it takes to know where we are to a meter. So we're already using that whether we know it or not, and it's actually much more important than even just knowing where you are. GPS is this precision timing system, and many more devices that we rely on GPS for its timing rather than just telling us where we are. So all our telecommunications, all our data centers, all our financial transactions are relying on GPS for precision timing. So the technology is already out there in the world, and what we're hoping to do with this next generation technology is to make that technology more resilient, make it more robust, and expand capabilities by improving the performance. On the same token, we can take a lot of the tools and techniques that go into making those atomic clocks, which enable GPS, and apply them toward sensing. So very precise measurements of rotation and acceleration that help us know where we are on the planet when we don't have access to GPS.
Great. Ryan, question for you. You sit in the middle of what I would call sort of the security, compliance, government, all of the policy around where we are today. And Matt already talked about the fact that we're kind of in a stall waiting for a reauthorization of the Quantum Initiative Act. How does your role cement how we will move forward as a country in terms of infrastructure?
Yeah, so I think Matt did a great job of laying out. So in 2018, during the first Trump administration, we signed what was called the National Quantum Initiative Act. That put about $1.2 billion towards research and development across the federal government. And it was a watershed moment. At the time, in 2018, the U.S. was light years beyond any of our allies or adversaries in terms of quantum R&D and moving towards commercialization. That act in 2023, September of 23, was due to be reauthorized, and we are now 27 months in for waiting for Congress to reauthorize that act. That does not mean that the work that's being done at the national labs through the NSF and certainly in the private sector has stalled by any means. All of our companies are making huge strides. We're hitting our technological benchmarks. We're working with our government partners. But as a signaling mechanism and thinking about long-term funding from the U.S. federal government, we are stalled. And during that time, since 2018, obviously the world has changed a lot in those 7 years. It's changed geopolitically, it's changed technologically, and our adversaries and allies alike have made billions of dollars of investments. We've seen global governments now invest somewhere around $55 billion in quantum. We've seen most of these countries and blocs create very coherent national or continental-wide quantum strategies that take advantage of the comparative advantages that each of those companies or regions has. And the U.S. has, I don't want to say we've fallen behind because we are absolutely still the leader, but from a policy standpoint, we need Congress to act. I think it's important to do that across the federal government. We need to reauthorize the National Quantum Initiative Act. We need to continue these investments across the DOE. During this time, my company makes quantum computers, so we do not do sensing or networking, but our biggest partners are the national labs and the government. And so that is a critical funding and signaling mechanism that shows our leadership to the world and allows us as companies to prove out all of the things that we're talking about in terms of reaching fault tolerance, doing things that no current computer can do, solving pharmaceutical issues, material science. We need the government as partner, and from a national security and economic security standpoint, it is really critical that Congress takes up the ball and pushes quantum forward as a real national asset.
Well, we certainly appreciate all the work that you're doing, and it certainly sounds like there's more
Clearly not
reason.
doing a good job.
No, you're doing a great job. But I think it double underscores the fact that we need to have more public-private partnerships to make sure that we're continuing to push through on the initiatives that we have, right? Jeff, you are working on the superconducting and the magnetic side. What challenges are you seeing, or where maybe is the inflection for you on quantum that is in the very near future?
I really love this question because I am so excited about this inflection point that we've hit with quantum technologies as a whole, whether it's compute, sense, network. We have finally had the breakthrough in understanding that we have a basis fundamental knowledge that we can now build on. Scaling up without that fundamental knowledge is impossible. And the milestone of achieving enough of an understanding of a technology, especially a critical emerging technology, not an improvement to an existing fully scaled technology, is one of the absolute biggest milestones to scaling up. And what goes hand in hand with that is an emphasis on basic understanding. There's no reason that any of us should sit in this room and believe that what we see out in the world and in the news about quantum technology is as good as it's going to get. We are going to see rapid improvements that go along with the scale up of quantum technologies. And I think it's really important to see beyond just the supply chains and the materials and the hardware and the software, that the tangible, visualizable things that represent quantum technologies when we say, what does it need to scale? And one of the most important and truly exciting things about quantum is that we are only scratching the surface on what we can use it for. And those types of questions are fascinating, because if we have a completely new mode of computation that can do things that our classical computers couldn't do, that question of what can we now use it for, what's going to push it into demand that makes it scale rapidly, those are critical questions just as much as the supply chain is. And one final thought on this is, I think when it comes to scaling quantum and breaking down barriers to see it be widespread in our society, is going to be bridging industrial gaps. And the example that I really love to use is what we saw artificial intelligence do to the magnetic resonance imaging community. This was a machine that's used to look inside somebody's body, and you say artificial intelligence, how could that make that machine even better? But truly it happened. We all watched it happen. Most MRIs on the planet now have artificial intelligence used to improve the image quality that comes off of that hardware. And I like to pose the same question. If we watched AI impact MRI that much in such a short period of time, what could quantum do for an industry like MRI, and how could that push us to widespread, full-scale quantum industries?
So quantum's happening. This isn't a hypothetical. And Amanda, you're working with the startups community. And when I talk to you, every time I talk to you, you've got another thing that is in commercial path to acceleration to really, get to a use end customer. And I'm asking, what is sort of the one or two use cases that you see right now that can prove to this gang that it is happening faster than most people think?
Yeah, as far as use cases, and MRI is actually a really great example. The next generation of MRI, we'll call it MRI 2.0, will be quantum. There is research happening in academia and in some private labs that are going to create the next MRI machine that's going to have greater sensitivities, longer lasting machines, being able to show so much more of the human body. And that, I think, is going to be a very transformational use case related to life sciences and biology. So some of the work that's happening in quantum sensing right now is being able to detect disease even at the single cell level. So one of the things we're working on actually is related to pathology. So I don't know if you know, but the way we do pathology is over 100 years old, the Prussian blue staining. So could there be a better way using quantum tools to be able to look at cells that are in the tumors, to be able to say this is a healthy cell or this is a disease cell, or this cell will become diseased one day? And that's really what's going to make it transformational. Now, of course, we talked a lot about space, and I brought this up before. I think there's going to be such a revolution in space as we heard of today, and their sensors are going to need to keep up. So having sensors that can go into rugged environments, or having sensors that can be miniaturized and that we don't necessarily have to have 8 or 12 different sensors because a sensor might fail, that we actually know these sensors are going to be able to go up to 500 degrees or 750 degrees Celsius and be able to take on high radiation environments such as space will be literally transformative. And I don't think that we're going to be able to have a big space race without quantum sensors.
Jamil, congratulations on the acquisition by IonQ of your company. We all heard from Niccolo earlier today, and he's really on top of everything that's going on. One of the things I want you to lean in on a little bit is why the government is so enamored with your technology, and what GPS prototypes you may have, or anything that you feel comfortable that you can share, because it's very important to our national security.
Sure. So yeah, the government is responsible for delivering GPS 24 hours a day, 7 days a week to the entire world, and they do it for free. It's this hidden utility that, like I said, is cooked into our daily lives now. And so they're obviously interested in maintaining that capability and potentially improving upon the capability. While GPS the use is so widespread, it's actually a fairly fragile resource. And if you go into active areas of conflict like the Ukraine, GPS is jammed over the entire country. So, neither the Russians nor the Ukrainians can make use of it. The US has planes that cost $3 billion. It has submarines that cost $10 billion. They'd like to know where those assets are. And there's a lot of interest from our adversaries in knowing, say, where those submarines are as well. And so for something like a submarine, it fundamentally doesn't have access to GPS. The signal doesn't penetrate. So what do? You basically do what the Boy Scouts do. You do something known as dead reckoning. You carry your navigation system with you. You very precisely measure your accelerations and your rotations, and from that you can infer where you are on the planet. So it's strengthening GPS is a big part of it. It is building systems that can operate in the absence of GPS is also very critical to the government. And as a result, they sponsor a lot of work in this area. So we were recently acquired. One of the novelties of our company, which is a quantum startup, is that we had no outside investment or debt. We were bootstrapped on government contracts. We started with a couple small business contracts, and we just worked our way up from $125,000 contracts to $1 million contracts to $10 million to ultimately $30 million contracts. And we use that to really develop this prototype technology that is now starting to go out into the world. We don't see our work, we don't see ourselves as a government contractor, we see ourselves as a commercial product company that is building technology that is very aligned with government interests. And so we were able to leverage that technology, and now I think we're excited to take what we've developed under the government and work toward productization.
Excellent. And Ryan, on the government other programs besides what we talked about with Congress with the reauthorization of the Quantum Initiative Act, what are the programs that kind of show us that the government is ready for this quantum technology and the quantum apps to be deployed immediately? And maybe you can hit on like NIST and a couple of the other names that we've sort of thrown out there that maybe the group doesn't know about.
Sure. So I'll start on the funding side. So aside from the National Quantum Initiative, which again is still due to be reauthorized, we've seen DARPA take a huge leadership role in quantum. And obviously DARPA is, most of the technologies that we use every day came out of DARPA in some form or fashion from the 70s through the 90s. Unbelievably innovative, important government agency. They are absolutely on the ball in quantum. They have what's called the Quantum Benchmarking Initiative, QBI. And what they're doing there is getting under the hood of dozens of companies in the quantum space, trying to get rid of the hype, figure out what actually the technology looks like, how the government can take advantage of it themselves, and how the government can help de-risk those roadmaps moving towards what we call fault tolerance, which is the point at which quantum computers are doing things that no classical computer can do. And so this is a critical funding mechanism from the US government, and it's also good for us as an entire industry because it keeps us honest, and it gives little breadcrumbs along the way, starting small amounts of money, around $1 million. Stage B has $15 million as an award, going all the way up to $300 million for the final round, which is going to be before 2033. This got a lot more funding in the Big Beautiful Bill Act this summer, and will be funded aside from any of the other issues coming from Congress. So this is a radically important program for all of us to be a part of. And it's good, too, to the investment community, the global community, to say, look, the US government, DARPA, has stamped this technology with their stamp of approval, and we're moving past hype. This is real use useful for both commercial industry and for the government as well. A lot's going on in the DOE. 2 weeks ago, DOE announced $625 million for some of their quantum test beds. So again, there's a lot going on at the federal government level. I'll echo some of the stuff that Matt said earlier in that because Congress is somewhat stalled on a lot of issues, we are seeing states and local governments absolutely step up, fund quantum, and figure out ways to tie public-private partnerships to bring in academic institutions and to build a quantum workforce. Because I think the reason why all of us care about quantum is because it's this exciting new industry. We don't really understand it. How do we make this economically viable? How do we make this something? We've talked a lot about space today. How do we talk about quantum today the way we talked about space in the 50s and 60s as a sexy career to go into that previously did not exist, as something that's vastly important for national security, for economic security, that can take a kid who might not be otherwise mathematically inclined, but open up this entire new world of a next generation, next industrial revolution. And so we're trying to figure out ways to do that. And honestly, states and local governments are doing a great job of that. I think South Florida will be a capital of quantum, and figuring out how to take the work that is being done across academic institutions, infuse capital and resources from larger quantum companies like ours, and then work with the state government to build ecosystems. Make sure that kids from K through 12 are learning what quantum is. Make sure we're not just thinking about PhDs, which obviously we hire a lot of PhDs, certainly, but we also hire folks from trade schools. We hire a lot of welders. We hire a lot of technicians. We hire idiots like me who are lawyers and do policy. You do not have to be a scientist to work in this industry, and we need to be much broader in how we paint and talk about quantum. The last thing I'll mention, and then I'll move on, is NIST. NIST is the National Institute of Standards and Technology. This goes to the cybersecurity piece that Matt mentioned. At some point in the future, I don't want to speculate about timelines, but at some point in the not so distant future, the magic that makes quantum computers able to help solve some of the problems around pharmaceuticals, material science, et cetera, will also break most of the encryption that our entire lives are built on. And so we've got to move all of our cybersecurity systems to be what's called quantum safe. NIST is the federal agency that is basically responsible for that. They have built a suite of algorithms that they believe to be resistant to future quantum attacks, and there's a lot of legislation, national security memoranda, and work coming out of the White House to push government and industry alike to move towards those standards so we can all be safe in the quantum era while also gleaning all of these amazing benefits that we're here talking about today.
So Jeff, we're marching forward and we're marching hard, right? So now what's the biggest barrier to scale? Is it workforce readiness? Is it science? Is it manufacturing? What do you think unlocks that industrial production, perhaps, obstacle?
It's a great question. It's the first thing that really comes to my mind is looking at our past. I don't think for a group like this, I need to describe in detail what we've experienced over the past in supply chains like rare earth critical minerals. The complacency over decades creates a vulnerability in these U.S. and allied supply chains that swing the door wide open for adversaries to use control of the supply chains as an economic weapon and undermine the supply of critical materials. And what happened in rare earth materials was complacency over the course of decades, leading to an urgency that absolutely required federal intervention. And avoiding something like that with an emergent supply chain like quantum is going to be absolutely critical. And I don't just point the finger at the government and say it is your responsibility for these supply chains to emerge. It is just as much on the private sector and private investment to drive the security of the supply chains. And when you think about something like quantum and you talk about hardware and you talk about the materials that make that hardware, it requires partnerships. And those partnerships, some of them may be from some of those other supply chains, some of them may be brand new partnerships that were never required before. But I think one of the biggest barriers to scaling up successfully is going to be avoiding the mistakes of the past on supply chains that are now very, very vulnerable and having to have the government go back and do emergency management of those vulnerabilities. I'll speak, from what my company does in superconductivity, which is in all ways a critical emerging technology, maybe really just behind the quantum supply chain and market emergence. And we do not see anywhere near the level of seriousness taken in the world of superconductivity when it comes to asking questions like, who's going to manufacture that superconducting wire that you're going to go build the magnet out of? Or where did you get the metal to make that wire? Where's the provenance going all the way back to who dug in the dirt to get the mineral out that ended up making you this complex cryogenic machine that can do something like an MRI machine or a fusion nuclear reactor that can do something that nothing else could do? And I think we have to really focus on this moment in time, because we will not get this moment back. If we're complacent and we take the path of the rare earth materials supply chain, we know where we're going to end up. So I think one of the biggest barriers to scale is going to really be taking a close look at the full provenance of those supply chains, going all the way back to the natural minerals, and then the partnerships that have the security long term for those supply chains to be able to support a real scale up.
So I'm going to stay with you. Can the U.S. become a leader of self-sustained supply chain for the quantum industry?
I absolutely believe it. I think we're well aligned to do this with the seriousness and investments that have been made. I think one of the intricacies that we really have to understand with quantum, and this was very similar in our world of superconductivity, is that when we say critical material, a lot of times we're not actually talking about traditional critical materials like gold or copper. We're talking about these strange metals like gallium or rubidium or ytterbium, stuff that, honestly, really from a commercial perspective, didn't have a lot of importance in a volume metric. Sure, with a little bit of it, you can turn a blind eye to where it came from, but for things like quantum, we're going to need large volumes of these kind of non-traditionally volumetrically important materials like some of the elements that I rattled off. And one of the solutions I really see to the U.S. becoming a leader is leveraging the investments that we've made already into traditional mining. And what I mean by that are the huge investments and activities that the U.S. and allied supply chains have had in things like coal mining or phosphate mining or copper mining. And the reason those are so important to a new supply chain in quantum is that when you dig that copper or that phosphate out of the ground, inevitably you are producing things like tailings or waste streams from that mining operation. And with no exception, but with a difference in what those waste streams contain, they always contain something valuable that we can use as a fully domestic resource with an environmental impact that's already been made. We've already dug it out of the ground once. We've already processed it once. We have these massive stockpiles from our traditional mining operations that give us a real shot at full domestic independence of a quantum supply chain, because the materials we've got are in our garbage. And if you look at it from that perspective, why not get it if we've already dug it out of the ground and it's sitting in our garbage, versus having all of the environmental impact and cost in digging a brand new mine just to try to get these less common materials out of them?
Jamil, every time I sort of go onto Quantum Insider and I start researching things that are newsworthy of the day, I see autonomous. It's there every day now. How is quantum and autonomous fill in the blank, whether it be freight, whether it be driving, et cetera, how is that being impacted by the technology that you see?
Yeah, I think it really is that these next generation of clocks will come along. So I haven't talked too much about what we do at Vector Atomic, but I told you the world is currently distributing time right now in 10 nanosecond increments. We're using a lot of the laboratory atomic physics technology that we developed as graduate students and postdocs several years ago, and trying to bring that to bear into real world devices. So we want to upgrade, our long-term vision is to upgrade the global timing backbone from nanoseconds to picoseconds, 10 trillionths of a second. And so that positioning that gives you, or that timing that gives you meter scale positioning, this next generation can give you centimeter scale positioning. And that will be important for autonomy. In the future, we're likely all going to be driving around in these autonomous vehicles. We'd like to know not just that they're on the road, but they're in the lane that they need to be in. And so that will play really a central role. So that is, really the primary piece. Within the DoD, in these environments where you might not have access to GPS, that's where we need alternative methods, and that's where we're developing what are known as quantum inertial sensors or inertial navigation systems. Also, sensors that measure gravity and can compare those measurements to a local map and allow you to navigate in the absence of GPS or other sources, or kind of navigate blindly. So autonomy is a huge part of this technology.
And Amanda, you're on the sensing side as well. You talked a little bit about use case, but what are some of the ways that you're deploying your quantum sensing right now?
So I mentioned before that our company has spun out 2 startup companies. So the first is called Euclid, of course with a Q, because everything is quantum. And that company is focusing on a problem within the semiconductor world. So semiconductors are advancing, as most things are, and instead of them being packaged as just a flat semiconductor, now in order to have more power and more processing power, a lot of the semiconductors are being packaged one above each other. Now the problem is there's no way to be able to detect if these semiconductors are positioned right or if the packaging is aligned properly. So things might come off the line where the semiconductors are being made and it just not be a good package, and it may just then be able to throw out so many of these semiconductors. I think the statistic is that the semiconductor industry is losing $10 billion a year just from this problem. So what Euclid has done is taken our quantum sensing tools and be able to create something that can look at the very, very small magnetic signals coming out of the packages and be able to map onto a screen then and say, here is exactly what's going on within this particular package as it's coming off of the production line. And then hopefully one day, and this is how hopefully quantum sensing will make some money for our investors, but that this tool will be able to be in line in all semiconductor fabs to be able to provide more information as these semiconductors are coming off of the fab, and then therefore be able to be deployed with a lot less errors. And the same type of technology can be used for electric vehicle batteries or really any other type of microelectronics as this technology advances. So Euclid, again, you can Google it with a Q, is just come out of stealth and then working with many semiconductor companies to be able to do this cutting edge research and deploy quantum now. So this is not something that most lay people would ever think of or just never come across it in our lives. So as quantum's starting to come up, and particularly quantum sensing, and you heard a lot about positioning, timing, GPS, we're not going to be seeing it. It's not that you and I are going to be holding a quantum computer instead of an Apple iPhone. These small incremental changes is what's going to make our lives better, and we're not going to even know that they're quantum.
Ryan, does quantum readiness become a strategic advantage, or like the semiconductor race, or is this really more of a geopolitical race?
I think it's unequivocally both, in that quantum is inextricably...
That's not an option, just... Sorry.
Okay.
It's
I'm
superpositioned. It can be...
Yeah, cozy.
Geopolitical versus what?
Well, it's strategic.
Okay, I'll go more strategic, but there's absolutely a geopolitical bent to this. Quantum is inextricably bound up in national security, and it will be. There's a lot of people in the government, on the Hill, otherwise, who the reason they care about quantum is because China has invested $20 billion in quantum. They worry about the encryption piece. So from my perspective, that's an asset. You can get that person on board to support the U.S. quantum industry because you have whatever, a shared enemy, they're worried about the national security piece. That's a win. If you also have a policymaker who's worried about domestic industrial policy, creating the workforce of the future, job training, more kind of classically domestic policy piece, that's a win too. And to kind of the point they were talking about in Matt's panel, quantum is unbelievably bipartisan. The problem is not that it's a Republican issue, it's a Democratic issue. It's very bipartisan, but it's just there is such a high learning curve, and we as an industry, I think, have got to do a better job of explaining this to the investment community, to the policy community, that one, quantum is here, quantum is now. Two, quantum is investable today. And three, quantum is a national asset that we've got to treat as important as AI, as semiconductors, et cetera. When we think about the data center of the future, when we think about everything that's in the news right now with OpenAI and Meta and NVIDIA investing in data centers, the data center of the future is high-performance computing plus GPUs plus quantum. We can create a more energy-efficient data center long-term if you build quantum into those data centers come 2030, et cetera. That's not ready today, but when we think about long-term domestic policy and when we think about building these use cases, quantum by itself will never be the answer, but quantum plus everything that we have learned and accomplished the last few years in the AI industry and 30 years of high-performance computing leads to better results for the commercial industry, better results for the national security objectives, and makes the U.S. the absolute leader alongside of our allies, where we are distributing all of these gains across our allies, but we've got to invest today, both from the government and the private sector.
I think it was you or someone in your camp that told me about a year ago that we could spend billions now or trillions in defense later. So that stuck with me for sure. Jeff, if we were to speak again in 2027, what advancements do you think on the compute side will be in place? So I'm giving you about a 12-month.
So I spent over 20 years doing research at a national lab for the Department of Energy and Department of Defense. So when I think about what do I think the future is going to look like on a 1 or 2 year time scale, I'm very reserved. I'm very conservative because I've seen how difficult it is to innovate when industries are young or industry is right around the corner and you're still in the research phase. So if I were to look ahead 12 or 18 months, I would really echo what Ryan mentioned as something that we're seeing evolve very rapidly. And it goes under different words. It's HPC quantum or hybrid compute or accelerated quantum supercomputing. But the notion is the same. It's tightly integrating a supercomputer to a quantum computer. And when you put the two together, you kind of get the best of both worlds. And the rapid advancement that we're seeing in this field, diminishing the power requirements of a data center, opening up completely new problems that it would be able to solve, and mutually increasing the effectiveness of both the supercomputer and the quantum computer, each one doing what it's best at doing. And the analogy that I kind of think about often and talk about with my colleagues and friends is this idea that you've got two skiers at the top of a mountain, and one of the skiers can barely see; it has no vision, but that skier is strong. It can ski faster than any other skier on the planet, and it is a brute force skier, just barreling down and knocking over the trees on the way, but so strong it just can do it. And the other skier standing next to that first one has the best vision you could possibly imagine, can see the best pathway down the mountain, can visualize it down to the millimeter where it needs to put its skis, but that skier has no muscle and can't go very fast at all. So when you put these two together, you end up with the skier that is the strongest and with the best vision to find the path down the mountain that is both the most efficient and leveraging all of the strength and horsepower. And when you think about that analogy, that very strong brute force skier, that's the supercomputer. It's a brute force approach to computation, and you can grind it out. No matter how hard it is, you can grind it out and approach that problem, but you don't know if you're actually doing it the most efficient way. And if you're looking for the right answer, like getting down a mountain, I have to test each of the routes to find out which one was the best one. The quantum computer is the skier that can see well, but doesn't have necessarily the brute force strength to compute, but does have the ability to look at all of those routes simultaneously, know what the best one is, and take that. So I really see that 12, 18 months out from now, I really think this hybrid HPC quantum compute approach really has the ability to move forward. And I don't think we're going to see it in the similar way that we see AI factories right now, where it's hundreds of megawatts or gigawatts of power required to fuel that brute force supercomputer. And I think we're going to see much smaller, much more tightly integrated and higher compute density supercomputers, coupled with a quantum computer that offloads an incredible amount of otherwise very, very costly, power-consuming supercomputation.
So I'm getting a little red dot, looking at me right now because we're running out of time. I think we could all sit here for 2 hours and talk about this, because the key takeaway that I want everyone to really, look at is that quantum is here. It's already happening. Applications are already in place. We've talked about some of what's happening, obviously, on the security side, the sensing side, the magnet side. Piece by piece, we're going to see more in healthcare. We're going to see more in energy. We're going to see more in defense. But it's clearly here. And I think that the big question is, are we going to be ready when this revolution hits us in between the eyes? Because it's not going to be, is it coming? It's when it comes, are we ready? And so talking to you all as professionals in the space is so empowering, because it gives us that conversation, because we really do feel that everyone needs to be educated about it. There's so much importance that's going to be behind public and private partnerships going forward, workforce readiness, everything that we can do within our communities. And it's something that obviously we're all passionate about. We also feel very strongly about lifting each other up. The one thing that I wanted to end this panel with is that I love working with the people on this panel and others in the quantum ecosystem, because everybody is sharing their resources to make sure that we are advancing this cohesively and as a community. And so for that, I thank you. You make me smarter at my job. And I thank you all for listening, and the panelists for engaging in this conversation.
Thank you.
Thank you.
Thank you, everyone.